3 coming out. So sick and tired of waiting for it. I played Half-Life 2 when I was in college, and I thought it was brilliant. So like, okay, Half-Life 3, any day now. Like 10 years ago. Did you play Half-Life 2?
No, they keep joking about Half-Life.
I know. I'm waiting for it desperately. Okay. You have to understand at the time how big of a game it was, because it was the first game that had really proper physics in it. Like proper behavior, you know. Like there's so many things you would take for granted now in first-person games. Like, you know, you would expect the buildings to crumble the right way, and you'd expect things to, you know, you expect to be able to interact with objects and move them around, you know, and that they should behave the way you would expect them to. But then, you know, that only really started with Half-Life 2. It was their physics engine that started it. And the game, the physics for the game was designed by a team of Trinity College maths graduates. Yes. They're number one, you know. So anyways, I'm waiting for Half-Life 3. Okay, Half-Life, the original. Okay, so we know that n equals n0 e minus lambda t. And we also know from math class what this graph looks like. Just like that. It's exponentially decreasing. So it looks this type of graph. Ugly graph, I know.
It's nice.
It's not really. But you did these graphs in maths class in semester 1. How to graph them. Yeah. I would like you to just do a quick sketch. So if you could write down this equation that we had in the last lesson, and just draw a quick graph like this. Now this graph is terrible because I should really write here time and yeah, thank you. No.
What's on the graph?
N. Oh, come on, look, this is obviously Y, and T is obviously the X. Giving me a hard time here.
What's the...
No, what?
X, Y intercept?
You know what this is. What point is this?
What?
Thank you, N0. But you see, he knew this. You're just trying to make me angry.
No.
Yeah.
I don't know.
Yeah.
I didn't
Yeah.
know. I'm so stupid.
No. This is not true.
What's the X?
Seriously? Are you trolling me or are you really asking?
That's fine.
You're really asking? It's the T. No, don't ask me what the Y is.
Is it like n naught or is it ln n naught?
No, we haven't talked about using logs at all.
So if the answer is like from this graph by the intercept?
Yeah, no, that gets its own lesson. Yeah. But you can see where this is going. Now, soon we'll have to look at logs. Yeah. Because that's what we did for the lesson on the capacitor. Alright, continue. So, what's interesting about this graph is that the time required for half the sample to decay is the same regardless of where we look. Now, if I give you some data, this will make sense. So, here's some data. Here's the time, and here's the number of moles we have. Okay. So at the beginning, how many moles do we have of the sample? 100 moles. How long until we have 50 moles? We have to wait 2 seconds, right? Okay. Let's pick a different starting point. Okay. Let's start here, for example. How many moles do we have here? 25. How long do I wait until I have half of this number? 2 seconds again.
Yeah.
So.
Oh, you see, everything same gap.
That's the point I'm making. The time you need to wait to half is the same no matter where you start. So here, How long do I wait until I get half? 2 seconds. Yeah? So, just as an example, I would like you to write this down, and just to write underneath this 2 seconds. You can see it halves every 2 seconds.
It's always 2 seconds.
Well, in this case, it's always 2 seconds, yeah. And I should remind you of something from maths class.
What?
Yeah, what? In semester 1.
I thought the GP.
GP.
Yeah.
It's like the or is a half.
Yeah.
Although not quite, because we have to jump 2 to get the half. But if you were to check, you would actually discover that this is a geometric sequence,
Yeah.
where the a is 100 and the or is root 2 over 2.
It's 2 over 2?
Well, for this example.
Yeah.
You said in the exam they want 3 significant figures, even if like the answer was 50.
Oh, you mean should you write down 50.0?
Yeah.
No, in that case it's okay. But I suppose it's best to be safe to get into the habit, so you should perhaps write down 50.0. So that when you're doing the exam, you're always reminded that it should be 3 in the answer.
Is it always 1 3?
Yes. Yes, for physics. Okay, did you copy this table?
Yeah.
Bruce, do you have this table? Why? Because I asked you to. That's okay, Bruce. I'm just trying to care about your learning, that's all. Alright, continue. Which number are you at, Way? Which one? 100? You're only starting.
No, I wrote the top part.
I still have to write the bottom. It took you this long to write 0 to 10.
Yes, please.
But kindergarten
I
students
know
can
the
do it
table.
quickly. Okay, right. Well, no, you can see every 2 seconds it halves. Like, to go from 100 to 50 is 2 seconds. To go from 50 to 25 is another 2 seconds. So for this data, it's 2 seconds.
So it's half-life is 2.
Yeah, that's what we're getting to. I'm sorry, Way, I'm going to have to continue. Next. So, what do we mean when we say half-life? So the half-life of a sample is defined as the time required for half the sample to become stable, not radioactive.
But after 2 seconds, like the 100 to 50 is stable.
No.
No, not yet.
No, the 100 to 50, 50 of it is unstable and 50 of it is stable. It's maybe it decayed and half of it became lead, something inactive, and the other half is radioactive or something like this. Because you know, what's an example? Like, Japers, I can't remember. Carbon-14. Carbon-14 is radioactive,
Oh yeah.
but it decays. But I'm not sure, I can't remember what it decays into.
Carbon 14 might be
I'll have to check. Anyways. Got this? Yeah. I think you do something like this in chemistry. The time for half a reactant to. Is it, no?
Yeah.
Did you? No? Okay, anyways. I think you will do something like this in chemistry. Continue? So, here's the formula that lets us work out half-life. We can kind of actually prove it pretty easily. So, if I say n equals n0 e minus lambda t, I want the time for half. So this would be a half n0 equals n0 e minus lambda t. Well, I can cancel the n0s. I can do log a half equals minus lambda t. But that's log 1 minus log 2 equals minus lambda t. What's log 1? So I get minus log 2 equals minus lambda t. So t equals lambda times t equals log 2. Is one way to write the formula. Or to be a bit more clear, you can say t equals log 2 over lambda. But because this is the time, the half-life, usually I might put a little half here to remind me that this is the time for half to decay. So this is the formula if you want to write it down this way. T half is the half-life.
Oh, where's
It's 0.
Do we disprove?
Do you know? No, not really.
But useful?
Yeah.
Yeah. Makes sense.
Yeah. Well, we definitely need the formula at the end.
Is this LN2 or LN minus 2?
LN2, yeah. You realised you shouldn't have asked that since you finished it. Yeah, that's okay. Because then it's like, well, what number is LN?
No, I thought it was like, you know how T has. I thought that there's LN2.
Ah, yeah, okay. That's okay. All right.
Is it at the end, the half-life?
No, it doesn't. Well, you mean mathematically or in real life?
Yeah.
In real life it does, because if you think about it, once you have one atom left, you can't half that anymore. So you can't say, how long till I have half an atom? Oh, well, no, I've reached the end. So yeah, it does have it doesn't continue to half forever, because you can't half a single atom. So eventually it'll stop. Yeah? And of course you realise these things are approximations, because like if you had, let's say you had 10 atoms, and the half-life is 2 seconds, well then how many atoms do I have now? 5. And now how many do I have?
2.5.
No, you can't have 2.5 atoms.
Why?
You can't have 2.5 atoms. You can't say,
I
have half a hydrogen. Can you?
But we can
No,
say
you can't.
we can say that.
You can't.
We can say that we can get that, but we can't say that.
No. What'll happen is you'll either have 2 or 3. And half the time it will decay into 2, and half the time it will decay into 3.
Oh.
So my point is, when we get to a very small number, this starts to happen. So then if you have 2, that will become 1. And then it'll either become 0 or stay at 1. But eventually it'll become 0.
But I thought you say it's exponentially decreasing. I thought they never touched the...
Correct. So this is an example in physics of where the formula we use is like a ideal or perfect, but doesn't 100% represent real life, because in real life, like here, it will touch the axis. Because really what's happening is, although we picture the graph like this, nice and smooth. In real life, it's more like this. You know, it's like steps.
So much truth.
Well, okay, maybe I'm being a bit extreme here, but you know, it'd be more like this. Do you get what I'm saying? So it's quite difficult to deal with this as a formula. So the price we pay for having an easy formula is that it's not 100% accurate.
Like, what if there's no like professional companies using like the red line formula?
Say what?
Like, do they use the formula from the red line?
Well, it depends on the scale. If you're talking about moles, then that's 10 to the 23 atoms. So it'd be inappropriate to use the red ladder, because you would need to be accurate to 23 places of decimal before it makes a difference. But if you're only talking about 10 atoms, you would never use the curvy line, because that would then be too inaccurate. With 10 atoms, the graph would look more like this, you know. So it depends on the scale. Okay, so we've got that formula. Let's have a look at a question here. Just the one question. Do we know carbon-14? Have we heard of carbon-14 before?
Yeah.
Carbon-14 is an isotope of carbon, and it's radioactive. Bad news for you. It's radioactive and it's in all of you. But only a little bit, so it's okay. Yeah. People don't realize this, but you know, you have radioactive materials inside of you. It's very small, but you have some in it. Carbon-14 has a very long half-life, 5,730 years. It means it will take 5,700 years before it becomes half as radioactive. So really, its half-life is nearly infinity. You know, it's huge. Decays very slowly. You know, if you were looking at a graph, okay, this is U, 0, and if you're lucky, maybe 100 years, and this is the activity, the graph would really look like this, because the half-life is so big it doesn't look like it's decaying. Now if you zoom out and go to 1,000 years, maybe you'll start to see it a little bit. Okay. Anyway, what is the half-life in seconds? Can you convert this into seconds, please? See what you get. Yeah, just type it in. It's fine. You know this now. You're not that hungry. You don't know how many days in a year. No, you do. You know this. What is it? Come on. Pick a number. I'll tell you if you're right. It is 300 and something, correct? Now, you see, you're thinking of a circle, 360 degrees. You're close. You're close. 365. Yeah. Yeah, we won't worry about those. Now you're thinking, how many hours in a day? Yeah. We got an answer?
When you count the months and days.
Yeah, so let's have a look. It's 5,730 times 365 times 24 times 3600. Close. Okay, so that's the half-life in seconds.
And when you multiply the 12 months, 7 days.
No. 24 hours in each of the days, yeah. Okay? Yeah. So next, part B, what's the decay constant? So, if I use my formula here, where's it gone? This one here, I can say the decay constant is log 2 over the half-life. Yeah? So for this question, it will be log 2 over the half-life, which I just worked out. So the decay constant is this number. If you can write that down, please. I was thinking it was nitrogen. Anyways, got that? Part C. The molar mass is 14 grams. How many moles in 100 grams? So can you calculate that? How many moles in 100 grams? Okay, grand. Now, carbon 14 decays into nitrogen 14. So as the carbon 14 decays, it becomes nitrogen 14, and nitrogen 14 is stable, not radioactive. In 100 grams, how long until you have only 25 grams? Okay, well, let's start off with 100 grams. How long until I have 50 grams? Yeah, how long do I need to wait? If I start with 100 grams and I want it to decay into 50 grams, how long do I need to wait?
To buy that answer.
Give it to me in years.
Years?
Yes.
573.
Thank you. 5730.
Ah, yeah.
Oh, yeah.
Now, if I have 50 grams and I want 25 grams, how long more do I need to wait?
By 2.
Another 5730. So if I want to go from 100 to 25, I'll need to wait 11,460 years. Only.
Wrong.
2 half-lives. 2 half-lives. Yeah? Okay. Lastly, so what you can do is you can use half-life to estimate how long to go from 100 grams to 1 gram, for example. So let's start off with 100. 1 half-life, what will I have after 1 half-life? 50. After another half-life? 25. After another half-life?
12.5.
12.5. After another half-life?
6.25.
6.25. 3.12 something.
13.
And then after that it's 1.5 or something. But then the next, whatever it is, because then the next one will be less than 1 gram. So I have to wait 7 half-lives to go from 100 to something less than 1.
GP question.
It's like a GP question. So roughly 7 half-lives. So if I just go back here. So to go from 100 grams to 1 gram, I'll need to wait 40,000 years.
In the exam, to solve this question, we have the GP.
No. In the exam, they wouldn't give you this one. They give you like this one, where it's an exact number, like 100 to 25. Yeah, they would do it this way in the exam. I just put an interesting question at the end. Okay, is that okay?
Yeah.
Yep. So, one question for you to do. Let me just stop the video.